We present Learning what to learn for video object segmentation. In video object segmentation, you are given a video and a reference mask for an object. The task is then to segment that object in the rest of the frames. It is a very challenging task, since it requires adaptation during inference to a specific object, using the very limited information from the reference frame. Early approaches construct networks inspired by architecture for semantic segmentation. These generally have a feature extractor and a decoder network. To adapt the network to the target, the popular approach was then to fine-tune the entire network on the reference frame. This, however, tends to result in overfitting to the initial appearance and slow run times. More recent approaches employ similar architectures, but instead of fine-tuning, they integrate target appearance models. While the rest of the network is kept fixed during inference, the target model handles the adaptation to the target. Compared to fine-tuning, these methods are both faster and more robust to changes in appearance of the target and background regions. A number of different target models have been proposed. A popular approach is to perform feature matching in order to compare reference features with features from the test frame. These methods are efficient and differentiable, which enables end-to-end training of the entire network. However, they rely on feature embeddings to be sufficiently powerful and generic in order to generalize to unseen objects. Learning such an embedding is challenging and requires a large amount of training data. In this work, we propose a new approach for video object segmentation. At its core is a few-shot learner that optimizes a compact parametric target model to adapt the network to the current target. Learning such target-specific parameters allows us to easily adapt to challenging scenarios during inference. Consequently, our approach can generalize to novel classes without the need of extensive training data. We further design the few-shot learner to be differentiable to enable end-to-end training of our network. Specifically, our target model is constructed from a single conv filter. The few-shot learner optimizes the parameters of the conv filter to predict the reference target mask. In subsequent test frames, the trained conv filter predicts an intermediate mask of the target given input image features. The mask is then refined by the decoder network, which predicts the final segmentation mask. So how should we design the few-shot learner? We want the few-shot learner to determine a robust target model. For practical purposes, it should also be efficient. And to enable end-to-end training of the network, the few-shot learner must be differentiable. To achieve this, we design an L2 loss between the target model prediction and the labels. The learner then predicts the parameters of the target model by minimizing this loss. To achieve fast convergence, we employ steepest descent iterates to minimize the loss. In the steepest descent algorithm, the parameters are updated by taking steps along the gradient direction. The step length is computed by minimizing the loss along the direction of the gradient. To our favor, the optimal step length is obtained from this simple closed form expression. Moreover, both the step length and the gradient can easily be computed with simple network operations, utilizing the convolutional structure of the problem. We can thus backpropagate through the few-shot learner during training. As we can see, the target model predictions are fairly accurate after only a few steepest descent iterations. The few-shot learner can easily be implemented as a network module which outputs the parameters of the target model. Our full computational graph can thus be viewed as a feed-forward network. Given a video with a reference frame, the few-shot learner first predicts the parameters of the target model. The learned target model is then applied to the test frame features to output a score map of the target regions. The decoder then refines this along with features to predict the final segmentation mask. Thus, we can train all components of our network, including the feature extractor and the decoder, in an end-to-end manner. We have now presented our differentiable few-shot learner and how it can be integrated into an end-to-end trainable network for segmentation. But in this work, we take the few-shot learning paradigm even further. Firstly, why restrict to a single conv filter? Instead, we consider learning multiple filters to, for instance, segment different parts of the object. Intuitively, by sending more information to the decoder, we should be able to increase segmentation accuracy. The question then is, how do we train the filters? Or how do we construct the labels for the few-shot learner? In this work, we propose to learn the labels. In other words, learning what to learn. To this end, we introduce a label generator which encodes the target annotation into a multi-channel representation. Ideally, this can provide a strong target-aware cues which guides the network to generate accurate segmentations. The few-shot learner can train the filters to predict this label encoding using the same strategy as before, but here it minimizes the loss where the labels are provided by the label generator. To further induce more flexibility to the few-shot learner, we include a weighting of the elements in the loss. Having equal weights for all elements might not be optimal for maximizing the final segmentation accuracy. For instance, it could be beneficial to assign lower weights to ambiguous regions such as object boundaries and instead let the segmentation network handle them. It might also be beneficial to give higher weights to regions of small objects as a way of balancing the data. To tackle these issues, we introduce a weight predictor that assigns importance weights to the activations of the few-shot learner loss. Thus, the weight predictor can guide the learner to focus on the more crucial regions of the labels. This is a visualization of our final computational graph, including the label generator and the weight predictor. Like before, this network can be trained in an end-to-end manner. Next, we describe our inference pipeline. We first note that the few-shot learner can easily be extended to handle multiple samples. This is achieved by creating a dataset of features and reference masks. The few-shot learner then minimizes the loss as a sum over the dataset. During inference, we first create an initial dataset consisting of only the reference frame. The few-shot learner predicts the parameters of the target model by minimizing the loss. On the incoming test frame, the target model predicts the mask encoding, which is utilized by the network to generate the final prediction of the target mask. This predicted mask is then used along with the test frame to create a new sample for the few-shot learner. Before the next incoming frame, the few-shot learner re-optimizes the target model on the extended dataset. The same procedure is repeated for all frames in the video sequence. This constitutes a simple yet effective way of adapting the target model online and make it more robust to changes in target appearance. We train our network on mini-sequences drawn from the YouTube-VOS and Davis video datasets. Using these, we apply the same procedure as in the inference stage to generate target mask predictions. For each batch in the training, we compute the segmentation loss using ground truth masks, backpropagate it through all components of our network, and then update the network parameters. We here show that learning what to learn has a significant impact on the performance of our approach. We evaluate on a validation set consisting of 300 sequences from the YouTube-VOS training split that was not included during training. When just using the mask as labels in the few-shot learner, we achieve a Jaccard score of 77.5. When including the label generator, we see a clear improvement. Finally, by adding the weights from the weight predictor in the few-shot learner loss, we gain an additional significant boost in performance. How do we compare to existing methods then? On the YouTube-VOS 2018 benchmark, we outperformed the previous best performing method SDM with a significant margin. Our method is also comparably fast, and it runs in 14 frames per second. Notably, when the training data is limited to YouTube-VOS, the performance of SDM is very much reduced. Our approach, on the other hand, still remains stronger than all previous methods. These examples demonstrate how our method can handle challenging video sequences with multiple objects, drastic appearance changes, and occlusions. Generating accurate per pixel annotations is time-consuming and therefore expensive. We therefore extend our method to also handle the simpler way of annotating the target with a bounding box in the reference frame. This is achieved by adding a simple bounding box encoder module. This module maps the bounding box to a label encoding in the same domain as the label generator. It can then be fed into our decoder network, which can output a segmentation mask. Here we see an example where we are only given a bounding box annotation in the reference frame. We apply our box label generator and decoder network to estimate the initial target mask. Our approach can then proceed as in the mask initialization setting by using the estimated mask as a reference annotation. If you're interested in our work, the code and models are available at this link. We end by showing some more examples generated with mask initialization.